Hello, good people. Welcome to the next video here. Before we move on, I just want to make sure that we understand the different notations for the derivative. We have two notations that are widely used, and they're credited to these two mathematicians. One of them is Lagrange, Louis Lagrange, and his notation is this prime notation that we've been using, right? So f prime of 2. So for example, f prime, the prime notation is what we call it, or it could be y prime, it could be, I don't know, w prime of 7, right? So whenever we use the prime, then that's a Lagrange notation. That's telling us to find the derivative at a specific value. Whereas the Leibniz notation looks like this, and can be translated to taking the derivative of something with respect to x. So I'm taking the derivative of some kind of function here. Or if you have the y equation, then we're taking the derivative of the y equation with respect to x. But it has this fraction-looking notation. We're going to go back and forth between both. If we're given a y, then we're going to use dy dx. If we're given a function f or g or h, we're going to use the prime notation. We'll just go back and forth. But I want to come back to the limits that we had done over here. I know some of you might have crammed them all into that little space. I apologize, I didn't give you a blank paper to write those in. But as we go through these three different examples, I hope you realize like there was a pattern to this limit, right? Once we did the first one, the second one kind of followed a similar pattern. The third one followed a similar pattern. And there were places where there were common processes going on. For example, notice the first and the last term always canceled, right? And then I always had to factor out an h, and therefore I was able to reduce that h out of the way. I was able to reduce the h out of the way, and then I was finally able to do direct substitution to figure it out. The moral of the story is, if it's the same process, then why don't we use this limit process, but instead of plugging in a 2 or a 1 or a negative 2, why don't we just leave it as an x so that at the end we're not getting a derivative value like this, we're getting a derivative expression or function or equation. And that would be more powerful because then it would be like going from here to here in one step. And so as you go to the bottom of the page, it says there's a limit that's going to give us an expression that calculates the instantaneous rate of change, or the slope of the tangent line, which we know as a derivative, of a function at any x value. And so I'm going to go ahead and write it here. That limit is this: to find the derivative at any x, not at a specific point. Remember, this is changing from a, which was a very specific value, a specific x coordinate. Now I'm putting in the variable. We can figure it out by doing the limit as h approaches 0 of f of x plus h minus f of x all over h. So what are we doing? We're finding a derivative function, not just a derivative value. We're finding a formula that if we know the x coordinate and we do direct substitution into whatever you see in x, it's going to give us the slope of the tangent line. So that's a little bit extra, right? Like extra in a good way, because we're able to find any slope, and we don't have to do it one at a time the way we did this one at a time over here on the sidebar. Now, under it, so this is the derivative function. Make sure you understand that's different than the derivative value. The derivative value is what we were doing on the side panel, where we had a specific x value, which I called a, and that helped us find the slope of the tangent line at that particular point. So the only difference between these two things is that here I'm going to leave it in terms of x so that my answer gives me a formula, whereas here I'm going to substitute a number so that I can get a value out of it, and that's the actual slope, but only at that point. So let me label here and say this finds the derivative function, a formula that'll find the slope of the tangent line for any x value. This is the derivative value. It only finds the slope of the tangent line at that particular x coordinate that we call A. So it's the derivative value at x equals A. So with this formula, we'll be able to create derivative functions. So we're going to try this formula right now. We're going to flip the page, and I'm going to do this formula for number 3. And then we'll pause there. We'll come back on Monday, and we'll kind of pick up from there. So what are we trying to find? We're trying to find f prime of x. In order to do that, I need to find the limits as h approaches 0 of f of x plus h minus f of x all over h. I usually tell students this limit has 3 terms, right? There's this term, there is this term, and there's this term. The h never changes. The f of x changes depending on which function you're given, and the f of x plus h changes depending on which function you're given. So when I go to the next step, I can, with all confidence, say that the denominator is h. But to figure these things, I might have to do some side work over here. So let me come over here and say f of x plus h. Now how do I figure that out? Well, I'm supposed to substitute this wherever I see a variable. Oh shoot, I see 2 variables. I'm going to have to simplify that, right? And then this part, f of x, well, that would be this formula that we were given, right? So what I can do is I can say I'm going to subtract this f of x, but notice there are 3 terms. So I'm going to put them all in this bracket because I'm going to subtract each of those terms. I need to subtract each of those terms. This other blue part, we're going to have to figure out here. Okay, so let's see. We're going to double this thing squared. So that's x squared plus h squared plus 2h. I'm sorry, 2xh. Minus, we're going to multiply 7 times each of these. So we have to multiply 7 times x, but then I have to subtract 7 times h. And then don't forget about that plus 1. Dang, this is getting really algebra heavy, right? And this is where some people kind of lose their patience, because we need to be very careful when we do this algebra. As I zoom in, we need to double all this. So that'll be 2x squared plus 2h squared plus 4xh minus 7x minus 7h plus 1. That is a lot. And all of this is what needs to go in this space, because that's what f of x plus h is, right? So I'm going to try my best to squeeze everything in. I am running out of room fast. Maybe I shouldn't have written the red part yet. Minus 7x minus 7h plus 1. And now I can say there's a subtraction in between this. Okay. This looks heavy. Like my head hurts heavy. Remember what I told you. If we do things right, this last term will cancel out with things over here. So if I'm subtracting 2x, that means this and this are going to be gone. If I'm subtracting 7 minus 7x, if I subtract minus 7x, that's going to cancel with minus 7x. And then this minus 1 is going to cancel with this plus 1. And everything went away in the red part, as it should. So therefore, we're going to go ahead and continue. And let's see how far we can get. So I have 2h squared plus 4xh minus 7h all over that h on the bottom. That looks a little bit better. I also notice that I can factor out an h from all of these guys. So that's what we're going to do. So the limit as h approaches 0, I'm going to factor out an h. Why am I doing that? Because I'll be able to reduce this, and now I can plug in a 0 wherever I see an h, not an x. Because if you look carefully, this is saying as h approaches 0. Plug in a 0 here, that's gone. So then the only thing left with is 4x minus 7. I'm claiming that this formula is the derivative function of f of x. If I want to find the slope of the tangent line at any point on this parabola, I just substitute the x-coordinate in there, and I got my slope. I got my derivative. I got my instantaneous rate of change. The purpose of Monday is going to be to practice this process because it's a little heavy, and we'll be using our whiteboards to get more practice in there.